Hi everyone, my name is Justin Cross and this is my submission for homework 2 for my Transport 1 class. The problem we were given was, say you have a cylinder with a radius r and you fill it with a fluid given height r as well, just to make it simple. And you start spinning it at an angular velocity omega. What is the maximum angular velocity that you can have such that the water gets to the top at height h without spilling out? Now, I do have a couple equations that we're going to use to start here. The first one, the change in pressure, so dp over the change in the radius, dr equals rho, the density, omega squared r, just like that. We're also going to use an equation from the basic equation of statics, p equals rho gh. Again, rho being the density and g being the acceleration due to gravity. And finally, we want to know what the volume of a cylinder is. So the volume of cylinder equals pi times the radius squared times its height, just like that. We're going to use all three of these equations to solve this problem. Starting with the first equation, we're going to separate and integrate it. So we start with dp, we move the dr over, we get rho omega squared times r dr. And from here, we can integrate both sides. So integrate here and integrate here. And we turn these r's and these p's into dummy variables of integration because our top integrand here is going to be r and p. And we don't want to get them confused. So this becomes an r prime, a dr prime, and a dp prime, just like that. And this is a pretty easy integral to solve here. So we go p equals rho omega squared times r squared over 2, just like that. And because you can only ever have one pressure inside one space inside our cylinder, we can set this equal to rho gh, just like here. So we get rho gh equals rho omega squared r squared over 2. We've got a red marker for some cancellations here. This row and this row, they both cancel out. And then if we move the g over, we get h in terms of r. So our height, I'm going to draw it out here, just like that. Our height in terms of our radius is going to equal omega squared r squared over 2g, just like that. And we're going to use this equation here pretty soon. What we want to find is a master equation that takes into account everything that we have on our drawing. So say we want to solve for this big h here, the total height. So we say h equals, we start with our original height of the fluid, r, minus, we will say the distance here between the initial height and the minimum height here. We're going to call this the dip, or d, just like that. So we do the r minus d, minus the dip, plus the height at a given radius, but we want our radius to be big R, so it gives all of this here, plus h at r equals big R, equals the total height. And that's what we want to solve for here. We know this R was given in the problem. We just solved for this h right here. All what we want to do now is find the dip here. And to do that, we're going to look at the volumes of both sides. So if we come back over here to our drawing and draw over here, we know that because we're not gaining or losing any mass, the volume is going to stay the same no matter what shape it's in. So therefore, we can say that the volume here, just like that, is going to equal the volume underneath this parabola, just like this. Now, we already know what the volume of the cylinder is. That's the equation right here. What we want to do is integrate underneath this curve to find the volume of what's underneath the parabola. And again, that's pretty easy to do. So we start with dV, the change in volume equals the height times 2 pi r dr, just like that. Now, we already solved for the height here, so we just plug that in. So we get dV equals omega squared r squared over 2g times 2 pi r dr, just like that. And again, we have some more cancellations, but these 2's cancel out. And we're left with dv equals, we'll say pi omega squared over g times r cubed, is r squared with this r combined together, dr. And again, we integrate both sides. This is from 0 to big R, just like that, to get the total volume. So we're left with the volume V equals pi omega squared times big R to the fourth over 4g, just like that. Now, because we know both volumes are going to stay equal, we can set what we just solved for to the volume of a cylinder. So if we look at this volume of a cylinder, we get pi times the radius squared. This radius is going to be big R, was stated in the problem, big R squared, times the height in this case is our dip, times d, equals what we just solved for. So equals pi omega squared big R to the fourth over 4g. And again, we have more cancellations here. This pi, this R squared cancels with this R fourth, and we're left with R squared here, just like that. Now in terms of d, what we wanted to solve for, d equals omega squared big R squared over 4g, just like that. And now we have everything that we wanted for this master equation here. So if we plug everything in, we have r minus d, what we just solved for, minus omega squared big R squared over 4g, plus the height at r equals big R, so we just plug in big R into the small r here. So plus omega squared big R squared over 2g equals height, just like that. And this is pretty easy to solve for omega, right? We just combine like terms and move this r over. So we're left with omega squared big R squared over 4g equals h, the height, minus big R. And then we isolate omega. So omega equals omega squared here, this is squared, equals 4g times h minus r over r squared. And then finally, bring this up here, omega equals, take the square root of this other side, 2 square root of g times h minus r over big R. And that is what we wanted to solve for. What we just did was found the maximum angular velocity at which we can spin our cylinder such that no fluid will spill out, but it'll reach the top.